In this lecture, we'll look at gas exchange in the lungs. In order to understand the movement of gases such as oxygen and CO2 within our bodies, we need to understand how we measure pressure. One way to measure pressure of the atmosphere is using a barometer. Here's a relatively simple barometer. It consists of a tube filled with a fluid. Part of the tube is open to the atmosphere, one end of the tube. And notice that air will now push against that fluid. In this case, the fluid is mercury. And so this is one force, and there's an opposing force, which is the weight of the fluid. And by measuring the height of the column of fluid, in this case mercury, we can then tell what the force is acting on the fluid. So for example, if we're at sea level, we have 1 atmosphere of pressure, and that's balanced by a column of mercury, which is a very dense fluid that's 760 millimeters tall. So we can refer to this as 1 atmosphere. That's going to be 760 millimeters of mercury. It's also referred to as torr in honor of Evangelista Torricelli, who invented the mercury barometer. There are other units that can be used to measure pressure. For example, 1 atmosphere is also equal to 101.3 kilopascals, which is the international unit. And what else? Pounds per square inch, of course, is another unit of measure for pressure. Another concept that we need to understand is that of partial pressure. Partial pressure is the pressure exerted by a particular gas in a mixture of gases. So for example, here we have a mixture of 3 gases, A, B, and C. And we can look at each of these gases individually. So for example, if we imagine a box and we have gas A, well, the molecules of gas A, which are shown in blue here, will bang into the sides of this box, and they will exert a pressure, P sub A. Recall what pressure is. Pressure is the force that's perpendicular to a surface area. And so it's so as these bounce into the wall, they exert a force on the wall, and it's per unit of surface area. So for example, pounds per square inch. Pounds is unit of force, and the square inch would refer to that surface area. So gas B also bounces off the walls of this box, and it exerts a force that's perpendicular to the wall. So it has its own partial pressure, P sub B. The same thing for gas C. It has a partial pressure, P sub C. Now, the total pressure of all 3 gases is simply the sum of all the partial pressures. So P sub total equals P sub A plus P sub B plus P sub C. According to Dalton's law, the total pressure of a gas mixture is equal to the sum of the pressures of each gas in it. And the partial pressure is the pressure exerted by an individual gas. What is the partial pressure of O2 in air at sea level? Given the following facts, the total atmospheric pressure is 760 millimeters of mercury, and air is composed of 20.93% oxygen. To calculate the answer, take 20.93, convert it to 0.2093, multiply that by 760. The answer is 159 millimeters of mercury. In addition to oxygen, our atmosphere is made up of nitrogen and CO2. Nitrogen makes up 78% of the atmosphere. There's another 1% of the atmosphere that's made up of noble gases such as argon. These gases, however, are typically lumped together with nitrogen. So noble gases are inert. Nitrogen at standard pressures that our body experiences is also inert. So we often just lump them together, and we state that nitrogen is 79%, even though that's technically incorrect. Oxygen is 21%, and CO2 is about 0.03%. When you add these 3 gases together, you then have the total atmospheric pressure of 760 millimeters of mercury at sea level. And this chart shows you how you would arrive at this. So you'd have oxygen, for example, being about 21%. You convert that to a fraction, multiply that by the barometric pressure, and you get the partial pressure of oxygen. And you can do the same thing for the other gases, and you arrive at a total of 760 millimeters of mercury. Of course, the atmosphere is not always dry. So particularly when we talk in terms of physiology, we have to take into account the fact that there's also water vapor, particularly as we look at the lungs of the human body. So we need to introduce another term, which is relative humidity. Relative humidity is the ratio of the amount of water vapor present in the air compared to the greatest amount possible at that same temperature. So for example, within our lungs, we have deep within our lungs, we have a relative humidity of 100%. This means that given the temperature of our core, the core of our body, which is 37 degrees centigrade, we can't possibly have any more water vapor than that. Any more water would just turned into essentially condensate within the lung. It would condense into a liquid on the alveolar surfaces and so forth within the lung. So the air in the lungs has a relative humidity of 100%. So if we take that into account, we now have a new equation, which is the total partial pressure. The total pressure, again, has to add up to 1 atmospheric pressure, 760 millimeters of mercury. But we can consider this the pressure now adding an additional gas, which is water vapor. But we still have the original 3, which is partial pressure of nitrogen, partial pressure of oxygen, and partial pressure of CO2. In order to do the calculation, what we need to do is first subtract, say we wanted to calculate partial pressure of oxygen, PO2, we would first subtract the water vapor pressure from the total atmospheric pressure. So if given what is the PO2, given that the P total, this wet total here, is 760 millimeters of mercury, and the vapor pressure or water pressure is 47 millimeters of mercury. To do our calculation, we take the atmospheric pressure, subtract out the pressure due to the water vapor, which is 47, and then multiply this by 0.21 if we're trying to calculate the partial pressure of oxygen. And our answer is that the partial pressure of oxygen is 150 millimeters of mercury. Note that this is lower than the value we found earlier when we didn't have any water vapor. When we had dry air, the partial pressure of oxygen was 159 millimeters of mercury. This lower number makes sense because now part of the total pressure is due to the presence of water vapor. So you would expect this number to be lower. And in fact, so this number is, we're getting closer to what the actual partial pressure of oxygen within the alveolar space within our lungs is. We know that we essentially have 100% relative humidity within lungs. And so this number 47 is the water vapor pressure at 37 degrees centigrade. So given that we have water vapor, this is going to reduce the partial pressure of oxygen from 159 to 150. And as we'll see in the subsequent slide, it's going to be reduced even further due to the diffusion of oxygen into the pulmonary capillaries. This is just a quick recap of what we talked about. The water vapor pressure, P sub water, must be considered when calculating the partial pressure of oxygen in the air and in the lungs. So for example, in our lungs, the pressure of water at 37 degrees centigrade is 47 millimeters of mercury. And then we could do the calculation at sea level and we get 150 millimeters of mercury for the partial pressure of oxygen. And we could also do this calculation if we wanted to know how much, what the partial pressure of oxygen was in, say, room air, and we wanted to take into account the fact that there is some water vapor. So for example, let's say the room is at 37 degrees, but the relative humidity is not 100, because that would be extremely high. Let's say it's 50%. Then you would multiply 0.5 times 47, and that would be your water vapor pressure. You'd subtract that out from the total atmospheric pressure, which is 760, then multiply that number by 0.21. As I alluded to earlier, the actual partial pressure of oxygen within the alveolar airspace is actually lower than the one value of 150 millimeters of mercury. In fact, the alveolar PO2 is only 105 millimeters of mercury. Why is it so low? Well, it's because there's a constant movement of oxygen from the alveolar airspace into the pulmonary capillaries. So you're reducing the partial pressure of oxygen within the alveoli due to that very rapid diffusion. And so it's quite significantly different. In fact, it's 105 versus 150. And likewise, if you look at you could calculate the CO2 in a similar way that we just did for oxygen. So we could calculate how much CO2 would be based on the fact that there's 100% humidity deep within the lungs. But then you'd find actually that number was wrong. There's actually a lot more CO2 within the pulmonary capillaries. In the alveolar airspace, and that's because of the constant diffusion of CO2 from the pulmonary capillaries into the alveolar airspace. And so it would be quite a bit higher than what you would calculate. This figure very nicely summarizes the things we've been talking about. Within inspired air, this would be the air in the atmosphere. Water vapor is variable, and so it would have a variable pressure. CO2 has quite a low pressure because CO2 makes up a fairly small percentage of the atmosphere. Oxygen has a partial pressure of 159 millimeters of mercury, and nitrogen is about 601, and the total atmospheric pressure at sea level is 760 millimeters of mercury. Within our bodies, in the alveolar airspace, the water vapor pressure is 47 millimeters of mercury. This is assuming 100% relative humidity. That is, the air is saturated with water vapor, and that, of course, is true within the respiratory zone. This number is also dependent on the temperature, which is 37 degrees for mammalian core body temperature. The CO2 level is quite a bit higher than it is in the atmosphere, and this, of course, is because CO2 is constantly moving from the pulmonary capillaries and into the alveolar airspace. And the oxygen partial pressure within the alveolar airspace is 105 millimeters of mercury. And this is relatively low because what's happening is oxygen is moving by diffusion from the alveoli and into the pulmonary capillaries. And so there's a removal of oxygen that's continuous. And then, of course, the balance of these partial pressures is nitrogen, and we have a total, again, of 760 millimeters of mercury. This chart shows the effects of altitude on partial pressures within the air and within the body. So, for example, at an altitude of 0 feet, which is sea level, the atmospheric pressure is 760 millimeters of mercury. The partial pressure of oxygen, and this is assuming dry air, is essentially 21. Oxygen makes up 21%, so you'd multiply 760 by roughly 0.21, and you'd arrive at about 159 millimeters of mercury. As we just discussed, the partial pressure within the alveoli is quite a bit lower at 105. And then the partial pressure in the arterial blood, this is blood that would be measured, say, in the aorta or another major artery, is about 100 millimeters of mercury. Now, keep in mind that this arterial pressure is the same as the pressure of the pulmonary veins. And this is because the blood comes back from the pulmonary circuit. It goes into the left atrium, then into the left ventricle, and right out into the aorta and the major arteries. And so there's no capillaries in any of that route yet. So there's no diffusion of oxygen away from the blood and into the body. And so the oxygen level is very consistent. So this is essentially the same as the pulmonary venous arterial pressure. And so we'll talk about these numbers more in subsequent slides. Now, what's quite interesting as you go up to, say, higher and higher altitude is, of course, the atmospheric pressure drops, which is what you'd expect. And then the partial pressure of oxygen in the air also drops. Now, these numbers can be arrived at very easily just by simply multiplying the total atmospheric pressure by, again, roughly 0.21. And the reason for this is it's always the oxygen is 21% of the atmosphere at most altitudes that we would think about from a physiological perspective. And that's due to mixing of the air. There's wind and so forth. So the gas percentages are the same no matter what the altitude is over a very wide range of altitudes. Now, of course, if you get to very, very high altitudes, then things start to change. There's slightly different percentages of gases as you get to, truly high altitudes. But at any, say, mountain or something like that, you would still, like if you went to the top of Mount Everest, you would expect that oxygen would still make up 21% of the air that you would be breathing at the top of Mount Everest. In the previous slide, we saw that the alveolar air partial pressure of oxygen was 105 millimeters of mercury, and we saw that the arterial PO2 was 100 millimeters of mercury. So you'll note that they're very close. They're quite close. We'll talk about why they're different, but for now, let's talk about why they're so close. So there's a near equilibrium between those two values. So this means that as the blood was leaving the pulmonary, the lungs through the pulmonary veins, they essentially almost got to the point where they had the same partial pressure as within the alveolar airspace. And why are the lungs so good at doing this? Because the blood, of course, remember, is going through the pulmonary circuit very rapidly, right? And yet we get to a near equilibrium between the alveolar airspace and the pulmonary capillaries in terms of partial pressure of oxygen. And the reason for this is, first of all, there's a very large surface area for the alveoli. So it's a lot of respiratory surface that's helpful for getting oxygen to diffuse into the body. And also the diffusion distance is extremely short. Remember, the epithelial cells of each individual alveolus is a squamous epithelial cell. They're very flat. There's often a fused basement membrane between the epithelial cell and the pulmonary capillary cell. And so there's a very short distance. There is some interstitial space filled with fluid too, but there's a lot of very short distances, so that this allows for rapid diffusion also. And similarly, everything that I just said about oxygen also applies to carbon dioxide. Carbon dioxide is able to also come into an near equilibrium. So, and this is again due to the very rapid diffusion of CO2 within the lungs. In order to understand what's happening in the lungs in terms of movement of gas, we need to understand what happens at an interface between air and liquid. So we have this term partial pressure, and we understand it pretty well based on Dalton's law and so forth, and when we apply it to a gas. But we can all equally apply the idea of partial pressure to a liquid. And so the best way to picture this is, imagine a situation in which you have a liquid, such as water, and then you have a gas above that water. And you allow these to come to a state of equilibrium. So you have a gas, let's say it's oxygen. These green molecules represent oxygen. Let's say the partial pressure of oxygen is 105 millimeters of mercury. I've just made that the same as the alveolar airspace partial pressure of oxygen. And let's say this is the liquid that's lining the epithelial cells within each alveolus. In order to get oxygen into our body, it first has to diffuse into that liquid. And then from that liquid, it goes to the epithelial cells and through the basement membrane and through the endothelium of a pulmonary capillary. But the very first step is this step. It has to get into the water to begin with. So at equilibrium, you'll have an oxygen molecule entering into this liquid, and for each one that enters, you'll have one that's leaving. And then what I've tried to do is actually draw this somewhat realistically. There should be roughly about 30 of these green oxygen molecules here and just one down here. And notice these volumes are supposed to be the same. The volume of the gas here is the same as the volume of the liquid here. So what's happening is that these are in equilibrium because oxygen is entering and leaving at the same rate. So there's no net movement of oxygen. And when you're in this state, you would then say, well, okay, this is the partial pressure of the gas, and the partial pressure of oxygen within the liquid is identical to this partial pressure. So it's still 105 millimeters of mercury, because this is the way we're defining it, okay? And this is actually a very clever way of defining the partial pressure, no matter what, whether you're in a gas or in a liquid, because it's useful in terms of telling us about the direction of net movement of a molecule, such as this oxygen. So in this case, the partial pressures are equal, and therefore there's no net movement. And so you can imagine situations. Let's say we took away this one molecule here of oxygen, then the partial pressure here in the liquid would be zero, and then we'd have net movement from the gas into the liquid. Okay, so the partial pressure doesn't actually tell you really that much about the actual concentration. Clearly, within a volume of gas here, there's a lot more oxygen than there is within the same volume of the liquid here. But so that's not really what partial pressure is telling us, but it's telling us about the direction of movement of the gas across this liquid and gas and liquid interface. According to Henry's law, the amount of gas that can dissolve in a liquid depends on a few different factors. First of all, solubility of a particular gas may be different. For example, oxygen has a low solubility within water, whereas CO2 has a high solubility in water. Temperature also has a big influence. So, for example, more gas can be dissolved in a cold liquid compared to a hot liquid. This is evident if you put a pan of water on the stove and you heat it up. Before the water comes to a boil, you see bubbles forming in the water. And this is because of degassing. So the gas is no longer soluble in the liquid, and so comes out in the form of bubbles. Finally, partial pressure has a large influence on the amount of gas that's dissolved in a liquid. If you have an interface between gas and a liquid, the higher the partial pressure, the higher the amount of gas that will be dissolved in the liquid. Okay, so we've talked about PO2 a lot, but here we're going to recap a few of the things we talked about. So if a gas and a liquid are in equilibrium, then the PO2 is equal in the gas and in the liquid. So for example, let's look at this picture here. Let's imagine we have a total pressure of 760 millimeters of mercury. Let's say we have a gas canister with 20% oxygen. The partial pressure of oxygen within this tank is 152. Let's bubble that gas into this beaker and let it come to equilibrium. In other words, we let it bubble for say 5 minutes, and then we measure the amount of oxygen within the water, and we get the value 152. Now, so essentially we're showing that we're coming to an equilibrium. We have the same partial pressure within the gas and the liquid as long as they're in contact with each other for long enough, and they can come to an equilibrium. Now, of course, just to reiterate, but this doesn't mean it's the same concentration of oxygen. Of course, clearly, within say a liter of the gas, there's a lot more oxygen molecules than there would be in a liter of the water. Okay, so a difference in PO2 between the gas and liquid will lead to a net movement of gas. So let's imagine we do something like we put this beaker now in a box, and we just pump, say, nitrogen gas into the box surrounding this beaker. Well, now there's a partial pressure of oxygen of 152 within the beaker and a partial pressure of oxygen of 0 in the gas. And so you can imagine what will happen. The oxygen will move down its partial pressure gradient from within the beaker and into the surrounding gas. And so that's another rule. Gas will always move down its partial pressure gradient, so either from the liquid to the air or from the air to the liquid. The PO2 of blood indicates the amount of oxygen dissolved in the blood plasma. Okay, so when we measure, let's say we measure oxygen within a sample of blood, we're measuring the oxygen within the liquid part of the blood. Now, we'll talk about this more in a second, but most of the oxygen in our blood is actually bound to hemoglobin. So we're not, with this sort of an oxygen meter, we're measuring the partial pressure of oxygen within the blood plasma, which is a measure of the dissolved oxygen. And that doesn't, it's not a direct measure. It won't tell you actually how much oxygen is actually bound to hemoglobin. We have other ways of doing that, of figuring that out. So a very important parameter for health is the arterial partial pressure of oxygen. Normally, that's about 100 millimeters of mercury, as we've discussed already, and that's, as we said, is a little bit lower than the PO2 of the alveolar airspace, which is 105 millimeters of mercury. Now, there are certain situations in which the arterial PO2 will be lower than 100 millimeters of mercury. So, for example, for climbers going to a very high altitude, it's going to be lower than 100 millimeters of mercury. In contrast, if you see, and you would expect that to be low, right, because they're at high altitude. In contrast, if you see a low PO2 at sea level, this may indicate that there's an impaired gas exchange. So that could be caused, for example, by pulmonary disease, depressed breathing due to anesthesia, or, for example, respiratory distress syndrome, which occurs in premature infants that don't have enough surfactant. Okay, let's test our understanding of partial pressure. At the top of Mount Everest, the air pressure is 253 millimeters of mercury, so that's the total atmospheric pressure. What is the PO2 in the alveolar airspace of a climber? To do this calculation, we take the total atmospheric pressure, which is 253 millimeters of mercury. We'd subtract 43 millimeters of mercury, which is the pressure exerted by the vapor pressure, water vapor pressure within the lungs of the climber. We can assume that they have 100% relative humidity within their lungs. And also we're assuming that their core body pressure temperature is 37 degrees centigrade. Then you take that number and then multiply it by 0.21. We're assuming that the atmospheric percentage of oxygen is 21%, and that's true, again, due to the mixing of air. And so we get this number of 43 millimeters of mercury. So that's much lower than the 105. And recall that this 105 was reduced from 150 when we took into account the water vapor pressure. So we're doing that here. So we haven't even taken into account, with 43 millimeters of mercury, we haven't even taken into account the fact that there's also going to be rapid diffusion of there's going to be diffusion of oxygen from the alveolar airspace and into the pulmonary capillaries. So the actual number, if you were to measure within the alveolar airspace, the PO2 would actually be even lower than 43 millimeters of mercury. So this gives you a little bit of an indication of exactly how incredibly difficult it is to climb to a peak such as Mount Everest without supplemental oxygen. I mean, it's just really at the very limits of what the human body could possibly do. As I mentioned previously, oxygen has a relatively low solubility in water. So if we were to just rely on dissolved oxygen in water, we wouldn't be able to get enough oxygen to our tissues. To get around this problem, we have a respiratory pigment called hemoglobin. Hemoglobin can bind to oxygen and carry it. So hemoglobin in us is found within red blood cells. And the presence of hemoglobin within red blood cells tremendously increases the ability of our blood to carry oxygen. So in our blood, oxygen is carried in two forms. It's dissolved in the plasma and within the red blood cell water. In other words, within the water within a red blood cell. But that only accounts for about 2% of the total amount of oxygen carried per unit volume of blood. Most of it, so 98% of the oxygen, is reversibly bound to hemoglobin. Furthermore, at a normal PO2 of about 100 millimeters of mercury, in other words, that's a normal arterial PO2, hemoglobin is almost completely saturated with oxygen. And the way we can quantify that is we take a ratio of oxyhemoglobin, which is hemoglobin that's bound to oxygen, to the total hemoglobin, and then multiply that by 100 to yield a percentage, and it's 95%. So in other words, with a normal arterial PO2 of 100 millimeters of mercury, our oxygen saturation value is 97%. In order to test our understanding of how oxygen is being transported, let's take the example of hyperoxia. Hyperoxia is breathing 100% oxygen. So this would occur in a medical setting, but it also occurs in these things called oxygen bars, which became trendy a number of years ago. So in an oxygen bar, a person breathes in 100% oxygen, and the idea is that they feel that this will help them feel better and so forth. So the question is, will this significantly alter the O2 content in a healthy individual? So if you're breathing 100% oxygen, this will in fact only lead to a small increase in the amount of oxygen bound to hemoglobin, because remember, we're already at 97%. And that's at 21% oxygen, right? And the normal oxygen we're breathing. So perhaps you might go up a little bit, but you can't really go up that much higher, already at 97%. However, if you look at the blood plasma, and you say at an oxygen electrode, and you're measuring the amount of oxygen within the dissolved oxygen, well, that would increase, right? So that would significantly increase. Now the thing is, that's only carrying typically the dissolved oxygen within the blood plasma, and within the water within the red blood cells only accounts for about 2% of the oxygen that's being carried within our blood. So you might increase that percentage a bit higher, but it's not going to really have a huge impact. So for a healthy person at sea level, well, I've kind of answered the question, haven't I? Will hyperoxia cause a large increase in oxygen content of the blood? Let's think about that. And then let's also take the question and look at a person that's at high altitude. Will hyperoxia cause an increase at high altitude? So the answer is, for a healthy person at sea level, hyperoxia will have a very small effect, because most oxygen is transported bound to hemoglobin, which is already nearly completely saturated. So again, changing that saturation level by a small percentage won't really lead to much of a significant change in the oxygen that's being carried. Now, it will increase the amount of oxygen that's being carried just dissolved in the blood plasma and the red blood cell water, but that's a pretty small amount to begin with, so you're only going to increase, again, by a few percentage points. It's not really going to have a very dramatic effect. There is kind of an argument that does make sense for an oxygen bar. Perhaps at high altitude, hyperoxia might be beneficial. This would certainly temporarily alleviate some of the symptoms of, say, acute mountain sickness. Okay, so we basically have determined that probably there won't be a very large effect of breathing 100% oxygen at sea level. There may, in fact, be a subtle effect, though, and let me explain that subtle effect. So if a person is breathing 100% oxygen at sea level, that will, in fact, elevate their blood plasma level of oxygen, right? So the PO2 will be increased, the partial pressure of oxygen. And so as this blood then goes around, the systemic circuit, gets to the systemic capillaries, there may be an argument that because of the slightly higher partial pressure of oxygen, there may be an increased rate of diffusion from the capillaries and into the tissue. Now that elevated level of partial pressure may not last very long because, of course, we just established that most of the oxygen is in fact transported in the blood bound to hemoglobin, and it's being carried. So this, even if there is an elevated level of oxygen within the soluble part of the blood, solubilized within the blood, that may not last very long because it's a relatively small quantity. But I should just point out that there is a little bit of an argument that perhaps there might be at least a little bit of a slightly increased rate of diffusion because of this increase in partial pressure of oxygen. And there's actually is some real evidence for this in healthy individuals, but the evidence is one of them is fairly extreme. So the longest time a person has ever been able to hold their breath voluntarily for a man is 24 minutes and 3.43 seconds. And the way he did this was he hyperventilated oxygen for about 20 minutes, pure oxygen, I should say, before holding his breath. So hyperventilating, of course, is breathing really fast and deep, and he did this for 20 minutes. So what he was doing was getting a lot of oxygen into his tissues, probably, in order to allow him to hold his breath for such a long time. Now, without hyperoxia, the world record is much lower than that. It's 11 minutes and 34 seconds without this extra oxygen. So this sort of crazy world record does give some credence to the idea that by breathing hyperoxia, you may actually be able to get more oxygen into your tissues, and that may actually, in this case, it was allowing him to hold his breath for longer. This figure nicely summarizes some of the things we've been talking about. Coming from the lungs, the partial pressure of oxygen in the pulmonary vein is 100 millimeters of mercury. It then goes to the left atrium and the left ventricle. Within the systemic arteries, it's still 100 millimeters of mercury because there hasn't been any diffusion of oxygen yet. Within the systemic circuit, within the systemic capillaries, oxygen, of course, leaves. And then within the systemic veins, partial pressure of oxygen is much lower. It's now at 40 millimeters of mercury. The blood goes into the right atrium and then the right ventricle. It's then pumped to the through the pulmonary artery, still 40 in the pulmonary artery, and then within the pulmonary capillaries, oxygen is picked up, and the PO2 reaches 100 millimeters of mercury. Note here that the partial pressure of oxygen within the alveolar airspace is 105 millimeters of mercury. Now let's look at CO2. So in the pulmonary vein, the CO2 is 40. It then goes to the left atrium, left ventricle, still 40 within the systemic arteries. Now, within the systemic capillaries, it will pick up CO2 due to the CO2 that's being generated by aerobic respiration. PCO2 is 46 in the systemic veins. Then the blood goes to the right atrium, the right ventricle, then goes to the pulmonary artery. It's 46 millimeters of mercury still. Then CO2 is offloaded into the alveolar airspace. Note that the alveolar airspace has a PCO2 of 40, which is lower than 46. So CO2 will move down its concentration gradient from the pulmonary capillary and into the alveolar airspace. And so now there should be less CO2, and then we have in the pulmonary vein PCO2 of 40 millimeters of mercury. One of the most commonly used instruments in a hospital setting is called a pulse oximeter. This is a device that clips onto the fingertip or could be put on the pin of the ear. And this non-invasively measures the oxygen hemoglobin saturation. It's a non-invasive test. It's fast and it uses light. So it uses light of different wavelengths. And basically it takes advantage of the fact that oxyhemoglobin, deoxyhemoglobin absorb different wavelengths of light. From this information, the device determines the percent of the percent oxyhemoglobin saturation. And normally this value should be relatively high. It should be in the 90s or higher. This value can be abnormally low if gas exchange has been compromised or if there's impaired lung or heart function. In this diagram, we can see that the blood flow through the lungs is equal to the blood flow through the systemic circuit. In other words, if 5.5 liters per minute is flowing through the systemic circuit, then 5.5 liters of blood must also be flowing through the pulmonary circuit. Recall that the systemic circulation pressure difference is about 100 millimeters of mercury. That's the delta P, and that's calculated based on the fact that the mean arterial pressure is about 100 millimeters of mercury, and the pressure within the right atrium is about 0 millimeters of mercury. So that's the difference, the 100 millimeters of mercury. We can do a similar calculation for the pulmonary circuit. In the pulmonary circuit, the pressure difference between the left atrium and the pulmonary artery is only about 10 millimeters of mercury. This is based on the fact that the pulmonary artery pressure is 15 millimeters of mercury, and the pressure in the left atrium is 5 millimeters of mercury. So what you can see here is we can do a comparison between the systemic circuit and the pulmonary circuit. The systemic circuit has a high pressure. It's about 10 times higher than the pressure or delta P within the pulmonary circuit. But recall that the blood flow, the volume per unit time, is the same between the two circuits. So in order to have the same amount of flow, but with a much lower delta P, the pulmonary circuit must have a much lower resistance to flow, and that's in fact the case. So the pulmonary circuit has about a 10-fold lower resistance to the flow of blood compared to the systemic circulation. So we can refer to the pulmonary circuit as being a low pressure circuit. It's about 1/10 of the pressure of the systemic circuit. And it's also a low resistance circuit. It has a resistance to blood flow that's about 1/10 that of the systemic circuit. Okay, so we've talked about the fact that the pulmonary vascular resistance to blood flow is very low. So the pulmonary circuit can be thought of as a low pressured circuit and also a low resistance pathway. Now, this low pressure is actually very advantageous. Recall that at the systemic capillaries, there's filtration of fluid. Fluid ends up moving from the blood plasma and into the interstitial space. Thereby, this actually forms the interstitial fluid. And the pressure that causes the movement of fluid out of the capillaries into the interstitial space is the blood pressure, also called the hydrostatic pressure. Now, since the pulmonary circuit has a lower blood pressure, it has and therefore has a lower hydrostatic pressure. This reduces that filtration pressure, which pushes fluid out of these pulmonary capillaries and into the interstitial space. And therefore, this reduces the possibility of pulmonary edema. Pulmonary edema is a condition in which excess fluid enters the interstitial space within the lungs, and then from that interstitial space, it may actually even enter within the alveoli, and it can impede diffusion of gases within the alveoli. So it's quite a serious condition. So the fact that the pulmonary circuit is a low pressure circuit, again, is advantageous because it reduces the possibility of this pulmonary edema occurring. Recall that systemic arterioles constrict when the partial pressure of oxygen in tissues is high. This because for a systemic arteriole, this means that there's enough oxygen getting to the tissue, and it doesn't really make sense to therefore send more blood to that tissue that's getting a lot of oxygen to begin with. And so this ensures that only tissues that really need the oxygen are sent a lot of blood. Okay, so that's what happens with systemic arterioles. Pulmonary arterioles do exactly the opposite. They constrict when the alveolar partial pressure of O2 is low, and they dilate when the partial pressure of oxygen is high. Let's see if we can make sense of this phenomenon. So let's take the situation where we have in a particular alveolus, right? We have a low PO2 and a high PCO2. First of all, what does that mean and what we're doing is we're considering the fact that there's many alveoli within the lungs, so they may not all be experiencing exactly the same thing. So if the PO2 is low and the PCO2 is high, this means that there may be poor ventilation of that particular alveolus. Perhaps there's not enough fresh air getting to it. So in this situation, when you have low PO2 and high PCO2, the pulmonary arteriole that serves the capillaries that go to this alveolus that's experienced this low oxygen, high CO2, will constrict. And so now there's less blood flow to this particular alveolus. And this actually makes sense because what's happening is this alveolus isn't getting a lot of oxygen. So there's really no reason to send a lot of blood to it because we won't be able to pick up that much oxygen because it's simply not getting ventilated as much. Now let's look at the opposite situation. Let's imagine we have an alveolus and it has a high PO2 and a low PCO2. That means it's being well ventilated. It's for whatever reason, it's getting a lot of fresh air and it's got a lot of oxygen. So this means we really should send blood to that particular alveolus to pick up the oxygen. And so the pulmonary arterioles serving these alveoli will dilate. So an increase in oxygenation status leads to an increase in vasodilation. And now we're sending a lot more blood to this particular alveolus. And that's a good thing because it's receiving a lot of oxygen from the atmosphere. So it's being well ventilated. And now we can pick up that oxygen and bring it into the blood. So again, this is exactly the opposite of what we experience or what happens within systemic arterioles. So let's talk in a little more detail about how this actually happens. The low oxygen depolarizes smooth muscle cells of the arterial wall by inhibiting the outward flow of potassium. So recall that we have potassium leak channels. So potassium is normally leaking out all the time through many of the cells in our body. And that tends to, the movement of positive charge out of a cell will tend to make the inside of the cell negative with respect to the outside of the cell. So if you inhibit the outward flow of potassium through these, well, they're not necessarily leak channels, but they're channels that are gated, in this case, by oxygen, then this would lead to depolarization of the cell, right? Because you have other channels like sodium leak channels that would allow for sodium to flux into the cell and depolarize it. Now, depolarization will lead to the opening of voltage-gated calcium channels, and calcium will enter into the cell, into the smooth muscle cell, which then stimulates it to contract. So again, the response of pulmonary arterioles to low oxygen levels helps to match ventilation. So ventilation is referring to the amount of oxygen getting to the lungs. And we need to match that with perfusion, which is the amount of blood flow going to a local area of the lung. So by doing this, vasoconstriction, for example, here again, we're showing an alveolus that has a it's getting poorly ventilated, and therefore it really shouldn't be perfused with a lot of blood. So we have vasoconstriction of the pulmonary arterioles going to this local area where this alveolus sits, and therefore we'll reduce the blood perfusion, and that matches the fact that there's poor ventilation. So if you're standing upright, then there's the effect of gravity on the pulmonary arteries, such that the pressure in the pulmonary arteries at the base of the lung is higher than the pressure in the pulmonary arteries at the apex of the lung. Now recall that blood moves based on a delta P, a difference in pressure. So this means that there's going to be more movement of blood, so higher blood flow through the base of the lungs compared to the apex when a person is standing up and the person is at rest. So, and if we can here in this figure, we can look at the example of the actual numbers. So blood flow is liters of blood per minute. In the apex of the lungs, we only have 0.07 liters of blood per minute, whereas at the base of the lungs, we get 1.29 liters of blood per minute. So the perfusion rate of the base of the lung is much higher than the perfusion rate at the apex of the lung. Ventilation rate is defined as air volume per minute, so liters of air per minute. So if we look at the apex of the heart, we see that the ventilation rate is 0.24, and we can look at the base of the heart, and the ventilation rate is 0.82 liters per minute. So recall that in the previous slide, the perfusion rate was much higher at the base of the heart compared to the apex. So we might expect that, well, the ventilation rate is perhaps higher at the base also. And it is higher at the base compared to the apex. But the difference is not great enough to make up for the difference in perfusion rate. In order to better quantify what's going on in terms of ventilation and blood flow, what we can do is take a ratio of the ventilation rate divided by the blood flow rate. So for example, if we look at the apex of the lung, the ventilation rate is 0.24 liters per minute. The blood flow rate is 0.07. If you take 0.24 and divide it by 0.07, you get 3.40. So that's the ratio of ventilation to blood flow. So this means that there's a lot of ventilation and not that much blood flow. The ideal ratio would be about 1, which would mean that for 1 liter of air per minute, we should have 1 liter of blood flow per minute. Now, if we look at the base of the heart, we do the same calculation, we find that the ventilation to perfusion ratio is 0.63. So this means there's really, again, ideally you'd have about 1. This means that we're having a lot of blood flow relative to the amount of ventilation. This mismatch is in fact part of the reason. Recall that the alveolar airspace partial pressure of oxygen is 105 millimeters of mercury. If we look at the arterial partial pressure of oxygen, it's 100 millimeters of mercury. So this isn't the only reason, but this is a big part of the reason for why it isn't a perfect match, why we don't get closer to 105. It's because of this ventilation perfusion mismatch, which is found within the heart, within the lung. And this is with a healthy lung. This is correct. This is a healthy young person with no other problems, no other diseases or anything like that. We're next going to look at disorders caused by high partial pressure of gases. There's a family of disorders that occurs with deep sea divers. As a diver dives under the water, for every 10 meters below sea level, there's an increase in pressure of 1 atmosphere. So in other words, there's a very rapid increase in the number of atmospheres as the diver goes down deeper and deeper. And one common thing that can happen is called oxygen toxicity. So if you're breathing, say, 100% oxygen, and you're at 2.5 atmospheres, well, that's a very high level of oxygen, very high partial pressure, and this can actually lead to oxidation of enzymes. It can cause damage to the nervous system. It can cause seizures. It can cause coma and death. So that's pretty extreme. And so one way of getting around this problem is to use gas mixtures with lower percentages of oxygen. So in other words, with normal air, we have about 21% oxygen within normal air. But what they do is they'll breathe a gas mixture if they're at extreme depth, in which they've replaced some of the oxygen with another gas. A typical one might be helium, because it's a very inert gas. Okay, there's also nitrogen narcosis. Normally, we've talked about nitrogen as being physiologically inert, and that is true. It's normally very inert at normal pressures. However, at high pressure, partial pressure, nitrogen can actually dissolve into plasma membranes, and it can cause what's called this nitrogen narcosis, which results in intoxication. So the person feels as if they're drunk. They also may feel drowsiness. So this is, of course, extremely dangerous underwater. And this can happen as a diver goes to great depth. And it's more than just depth. The amount of nitrogen that builds up in the body is dependent on depth, but it's also has to do with the amount of time spent underwater. So a diver would have to pay attention to that. Another type of sickness is called decompression sickness. This occurs when a diver comes to the surface too fast. So again, as a person spends time underwater at depth, there will be movement of nitrogen from the air they're breathing into their blood plasma, and from the blood plasma into the tissues of their bodies. And so this is an effect that's dependent both on the pressure as well as the amount of time spent at a particular pressure. Now, if the diver comes up slowly, then there's sufficient time for the nitrogen to be expelled as they breathe, and large bubbles don't form in their tissue and in their blood. But if they come up very quickly, then this can lead to the formation of nitrogen. There's just simply too much nitrogen in the blood, and it can block small blood vessels. And so this can be extremely painful. It can really be quite disastrous. And so one of the treatments for this is to put the person in what's called a hyperbaric chamber. So you put them back into a situation in which you increase the pressure, and that makes the nitrogen go back into solution. And then once that happens, you can very gradually bring the pressure down. And again, they're able to, over time, breathe out that excess nitrogen without any harm. So decompression sickness can also potentially happen in airplanes. So as we fly from place to place at high altitude, the cabins are actually pressurized. And however, if there's suddenly a depressurization event that occurs in an airplane, then this could also lead to this decompression sickness, which is also referred to as the bends. So with a situation like a decompression sickness, people are often put in a hyperbaric chamber. In these chambers, the patients breathe 100% oxygen at 2 to 3 atmospheres of pressure. This does not increase the amount of oxygen carried by hemoglobin when compared to when breathing at sea level. Recall that when breathing at sea level, which is at 760 millimeters of mercury and 21% oxygen, the hemoglobin in arterial blood is already pretty well saturated. It's about 97% saturated. It does, however, significantly increase the amount of oxygen carried by plasma. So, for example, if you have this extreme 100% oxygen at 2 to 3 atmospheres, you can go from 0.3 milliliters of oxygen per 100 milliliters of blood at sea level to up to 6 milliliters of oxygen per 100 milliliters of blood. This is for 100% oxygen at 3 atmospheres of pressure. So that's now quite a significant increase in the amount of oxygen that's now being transported within the fluid itself. So this hyperbaric oxygen therapy can be useful for a number of things. Decompression sickness, we've already mentioned. It can also be used to treat gas gangrene. So gangrene may be caused by anaerobic bacteria. So an increase in oxygen partial pressure will kill those anaerobic bacteria. Carbon monoxide poisoning is a situation in which carbon monoxide binds with the hemoglobin at the same site where oxygen would normally bind, and it actually binds with a higher affinity than oxygen does. Now, so in order to get that carbon monoxide to come off of the hemoglobin, which is quite difficult, you need to replace it with oxygen. And so this is where the hyperbaric oxygen chamber would come into play. You'd have so much oxygen that it would essentially compete with the carbon monoxide and be able to restore the hemoglobin. It can also be useful for certain traumatic injuries, such as certain crush injuries. Again, you may have tissue that's not getting enough oxygen. It's hypoxic. And so increasing the oxygen delivery to tissue can be helpful. And it can also be, finally, hyperbaric oxygen therapy can be useful for certain inflammations and diabetic sores.